All right, good morning and happy Monday, fourth graders. Today we're going to do a specific study that is not necessarily in your Eureka math guide or handouts. This is something that I prepared for you because I feel like it's an important point in time to stop and reflect at what we're learning with regard to angles and as we're approaching planes and the study of the geometry there. First thing I want to look at today with you is the study of the circle. The circle is our friend, and as you saw in the previous video from BrainPop that I recommended, there are some special characteristics that are important for us to know, memorize, and be able to understand through analysis. So put on your scientific hats right now and join me in our math magician skill work here we're doing. So the first thing we want to do is have a protractor handy. So as you hold your protractor out, you'll remember that there are two ways to go about measuring angles, and angles being the measurement of degrees and not length. We want to keep that in mind. Help us to understand how things are measured on a rotation. So when we look at a circle, you could think of many things that are practical, maybe a wheel on your bike. Maybe you can think of a donut. Hey, like what you're looking at here, that could make you hungry and look and think about a donut. Could make you think of a number of things that have this pattern that we call the circle. The first thing I want to highlight to you and point out right now is we're looking at this specific arrow here that I have. And in that arrow, it's pointing to a starting point. And on your protractor, on the standard protractor, you see that it usually will start in this section, which I'm going to highlight here. And this section that I've drawn some etchings on is essentially quadrant 1 in geometry. And that's on a XYZ axis or plane. So I'm just introducing some ideas here as we move in this fashion as you get more and more deeper in mathematics with these quadrants, and they're called quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So I just want to point out that those exist, and that's how mathematicians will usually think about the circle and how to study measurement as it relates to where it started all. And the ancient study of the circle begins with something that you know is a symbol, and you've seen this before perhaps, which is pi. So we play with that term because pi represents a ratio between some parts of the circle. And that's really all I need you to know at this moment. Okay, so I'm going to go ahead and start us off clean. And today we want to understand the importance of something we call benchmark angles. And these benchmark angles are important for us because they help us understand how things work in terms of the circle and turning. So if we started out, which you're familiar with this point here on the circle, then you see it's 0 degrees begins our measurement in this position. So we're starting out here on the dial, if you want to think of this like a dial on a radio or a digital dial or something in the car, think of that. A benchmark, we want to use this as these are common angles that are standard for when we measure. And so when we're looking at these benchmark angles, we want to know how to connect and relate them to something that we're looking at, visual. So the first benchmark angle that I want to point out is, of course, we say we start at 0 degrees, but then we end up at something we would say would be 30 degrees. So I'm going to put my protractor down, and as you see, I've placed a mark here. So that would be our benchmark angle, the first one I want you to be aware of. Okay, so as we make that connection from 0 to 30 degrees, this one right here is 30 degrees. Okay, so that's the first one. So we'll list that out, these common benchmark angles. The next one would be an increment of 45 to 45 degrees, so that's 15 plus 30. So that gets us to our next benchmark, and that would happen to be, yeah, right here. Okay, so that one would be an additional, and so this will go ahead and measure from 0, and then we go up to this point, and that's 45 degrees. Okay, then the next one would fall into adding another amount, which would be another 15 degrees. And that one, let's just measure around the curve, and we end up here. Okay, so we have, these are ones that are common. Of course, you notice that the increments after 45 are going by about 15 degrees. And then we get into our positions that are, we call it quarter turn positions. So that's our 90 degree. And then we repeat ourselves again as we divide that up, and then you end up at 135, which is about right here. And then you're back at the straight angle, standard position at 180. And then when you pass that point, you get into the realm of reflex angles. So as you continue past 180 in this direction, then you're going to have 270, and then back at 360. So notice I just added the 36 to the 0. So really you can think of this as 360, or our starting point, 0 degrees. Okay? So we want to play with these angles and see what happens. So we have a 30-degree angle, a 45-degree angle, a 60-degree angle, and they're all based off of increments of 15 degrees. An increment is a movement, or you want to say rotation amount, that is common. That's a subset, a portion of these other common benchmark angles. Okay? So what does this all have to do with what we're practicing using the protractor? Is if you can think in sets or parts, then you can decompose them or compose them back together again quickly and be able to spot common angles that happen. So let's take a look at using our fraction and division. If you want to think of pizza, for example, most people are going to divide a pizza up into maybe 8 slices perhaps. So where would those 8 slices be on this pizza? Well, let's change this idea into a pizza. Well, firstly, we would know that we'd have our first cut, which would divide the entire pizza in half. Then we would cut it again into quarters, right? So what are these quarters representing? 1/4, that's our fraction value, which is going to be, we know, is 0.25, right, for our decimal equivalent. And then it's common for the pizza place or yourself at home to cut it again. So let's go ahead and slice from the 45, and once again here, so we divided it again. So now we have, if we count them, starting with these sections, we have 1, right, 2, 3, 4, 5, 6, 7, 8. So, and I'm talking about, each of these portions that are cut. Okay. So if each section is divided in that, then we know this has some relationship with the 45-degree angle, because if you have quarters and then you cut the quarter again, what you're doing is really saying, I'm taking 1/4 by 2, which you know you can say is the same as 1/4 times 1/2, and that gives you 1/8. Okay? So 1/8 is represented by this 45-degree angle. So there's some kind of relationship here that I'm wanting you to recognize between a 1/8 portion of a whole circle and the 45-degree angle. Okay? Another thing I want you to think about is how many quarter pieces make up a whole? Well, that would be easy because we remember how we might think of currency or money. So you ask yourselves, well, one whole is represented by the number 1. And if that's the case, then how many of these quarters which is represented by, we're talking about a 90-degree turn, is going to make up a whole. One whole, and we call this a revolution. So one revolution around the entire circle is that skateboarder that does a 360 trick, 360 turn. We're talking about going from here and all the way around and ending up back here at 360 degrees, right? So that's the revolution that we're talking about. So how many 90-degree turns would it take to get to one revolution? That's our statement. And the question would be answered by saying, well, 1/4 times 4 is going to equal to 1 whole. So that means we have, the idea is 90 degrees. We have to move in 90-degree turns 4 times. And what's 90 times 4? Is 360. So there's our proof that 4 quarter turns equating to 90 degrees each is going to give us a full revolution of 360 degrees. Likewise, if someone were to ask you how many of these 45-degree turns would it take for one revolution? So 45 we saw as a half of a quarter, correct? So then that's becomes 1/8 of a turn. So think about, I'm going back to the circle up here, this 45-degree amount right here, right? That chunk right there. How many of those turns would it take to make a full revolution? And it doesn't take too much rocket science to see that we are talking about there's one 45 degrees, there's another 45 degrees, another one here, another one here, 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 and here. So we can count them up. We have starting with 1, 2, 3, 4, 5, 6, 7, 8. Okay? So we can close out our statement by saying there are would give us 45 degrees. We rotate and 8 times in that amount, and then we get 360 again. So there's our evidence of that happening. So the idea here is, if anybody were to do real world measurement and practice of angles, your goal is to relate that to different types of movement or turns, measurements on the circle. And my last challenge to you would be to say, well, how many 30-degree turns or movements, would it require to be 90 degrees? Okay, so let's just ask yourself, if you had 30 degrees times an unknown, how many times would you have to move in a clockwise or counterclockwise turn to get to 90 degrees? And we can look at our circle again and say it would be 30 degrees. Then we would have to have how many increments? So looking back at the circle, let me choose a color that I haven't already clouded up our diagram with. So there's that 30 degrees right here. Here's another 30 degrees here, and another 30 degrees here. So we have, therefore, 3 degrees of movement at 30 degrees each, which would equal to 90 degrees, which would therefore end up giving us that right angle. Okay, so there's different ways to look at this, but if you can remember the importance of these benchmark angles, then that will help you to connect how angles are measured and common angles, and then be able to decompose them quickly so you can find particular angle supplements or complements, and even as you get further into the study of degrees. So leaving you with the close of this in this lesson is our goal was to study the circle and understand how 360 degrees is made up by 360 individual degrees of 1. So that's why how many times can 360 be divided by 1? It's going to be 360. So each degree, if we look super closely here, right, we're starting out 0. That first degree of movement is just going to be down here somewhere. So that would be considered like a 1 degree of movement. And then if you add them all up, then at some point, if we did it correctly, then you would get up to about 45 degrees up there. Okay, so the idea is 360 of these small hash marks around the entire circle. Therefore, we have this concept. Okay, so I want to close with the big ideas that you should reflect on and know from this lesson. Our target was to understand that 1 degree of rotation is equivalent to 1 out of 360, and that's we're talking about degrees here. So that is 1 rotation out of 360. Then how many of these degrees would it take to equal to 360? Well, we know, therefore, it would be you doing some fractional math, which is 1 over 360 times how many degrees? 360 degrees, which would be 360, and that equals 1 whole revolution. Okay, so that would be our understanding. The second point is that if we think about benchmarks, let's say 45 degrees, how many 45 degree rotations would give us a complete revolution? And we know 45 degrees is equivalent to, let's say, 1/8 from our pizza analogy of a slice. So 1/8, we know we'd have to have 1/8, 2/8, 3, 4, 5, 6, 7, and 8. So 8, it would take 8 times 45 degrees. So 8 of these movements to equal to 1 or 360 degrees. And that's 1 revolution. Okay? In the same manner, if we think about quarters, we know that's a benchmark or a special angle. So 90 degrees of a rotation is equal to 1/4. So 1/4 times 4, we know is going to be 4 over 4, which is 1 revolution